Hello people, how are you doing? Today I'm going to solve some problems regarding internal forces, and I found this one which is kind of interesting. And the reason I brought this problem is because instead of having just one element, now we have two members. You see, this is a two-member frame basically here. So the problem is determine the normal force, shear force, and moment at the section passing through the point D. Right here of the two-member frame. Okay, how do we start this? Because if we start this in the traditional approach and we just don't pay attention and we just don't realize what is happening here, then this is a pin and this is a pin, so that means that we're going to have two reactions and two reactions here. That's four reactions. Four reactions, three equations. That should be statically indeterminate, but it's not. That's not statically indeterminate. Remember, the other way of looking at this also is two reactions plus two internal forces. There are 2, 4, 6. 6 is R, 1, 2N. So R equals 6, N equals 2, and R equals 3 times N, which means it's statically determinate. Or, instead of even doing that approach and that evaluation, we can just look at this member. Look at this element, the element BC here. Basically what we have is a double hinge element. You have a hinge here, you have a hinge here, and you don't have any intermediate load. That was the definition of two-force member. Exactly that. So if you have that element and this element, this part here of the same element, I mean, this portion, the only way this element can be in equilibrium is if the forces are acting collinearly, like that. And if you know that, then we can transfer this to the element AB. So if I'm going to make a free body diagram of the element AB by cutting at D, actually what we will have is this. This is the trapezoidal load. This is the trapezoidal load here. And so this is the trapezoidal load here. And we have the reactions at A, vertical reaction at A, AY, and horizontal reaction at A, AX. This is 200 Newton meter, and this height here is 400 Newton meter. And the force of this CV is going to come in this direction, and it's going to be only one force in this line of action, like that. So I can put this and call this RB. Now if you look at this, how many reactions do we have? We have only 1, 2, 3 reactions, so that means that perfectly we can solve this problem. Let me just express this RB, and you know this is going to be the vertical component and the horizontal component of RB. So I'm going to need this angle alpha over there. That angle alpha is going to be the inverse tangent of this angle alpha here. Is going to be the inverse tangent of 2.5 divided by 6, which means alpha is equal to 22.62 degrees. Okay, now that we have this, we can start our problem by doing summation of moments at A. Just for the sake of facilitating our job, let's break this load in a rectangular distributed load and a triangular distributed load. If this is 400 from here to here, and this is 200 from here to here, that means that the height of this triangle is going to be 200, because the height of the rectangle I already know is 200. And that means that for effects of calculating reactions, I can place a vertical load for the triangle and a vertical load for the rectangle. This load is going to be 200 times 6, because remember this distance is 6, is here. 200 times 6 divided by 2, which is the area of the triangle, and that's 600. Remember, all of the loads are in Newton. And this other load here from the rectangle is just 6 times 200, which is 1200, 1200 or 1200 Newton. The application of this load for this vertical load from the triangle, this distance from here to here is 2/3 of the base, and the base is 6, meaning this is going to be 4 meters. And for the rectangular concentrated load, or the rectangular equivalent load coming from the distributed load, this is going to be half of the base, which is 6 divided by 2, 3 meters. Now that we have this, the rest of that for calculating the reaction is just simple operations like we did before. Let's do summation of moments at A equals 0. If I do moment here at A, the first thing that we encounter is this 1200 force, which is going to be acting negative. If I press here with respect to this point, it's going to be acting negative. So negative 1200 times the distance, and the distance is 3. Negative also 600 times the distance from here to the load, which is 4. And then I have the vertical component of RB. The horizontal is passing through the point, so that means that it doesn't produce any moment at point A, because it's passing exactly through here. I don't have this thickness. If I have this thickness and the problem making a statement about this thickness and the point A is below, then it will, or above, then it will produce. But in this case, the point, the load is applied exactly at the center, which is right here where the support is also at the center. So be careful with those distances. Sometimes that distance has to be taken into account, but in this case it's obvious that passes through the same axis. So we don't have to take that horizontal for anything. The vertical for this one is going to be, first of all, it's going to be positive because it's going to be acting in this direction. And secondly, it's going to be plus, then RB, but it's going to be RB sine alpha, because it's the opposite to the angle. That's the value of the force, times the distance, and the distance is 6. That has to be equal to 0. From here, I know alpha, I just calculated, I put everything together, and I can get that RB is equal to 2600 Newton. And once I have that, I can do summation of forces in X equals 0. And then AX plus RB cosine alpha equals 0. RB, I know it. Alpha, I know it. And that means that AX is going to be equal to negative 2400 newtons. And that negative means that this load, remember, is coming in the other direction, in the opposite direction. So AX is 2400 newton, and it's acting in this direction of A, to the left. And if I do summation of forces in Y equals 0 in the same section, then we have that AY minus 1200 minus 600 plus RB sine of the angle equals 0. And I know RB is 2600 and alpha is 22.62. So from here I can calculate AY, and AY is equal to 800 newtons. The only thing that we have done so far, is calculating the reactions. Now, once I have the reactions, I can come and make a section at the point D, which is my point of interest here. Because I already had these two reactions, or I have this reaction, whatever side I'm going to use, I haven't decided yet. So let's do that. Now let's get that section over there of the element, and I'm going to make a section here. If I make that section over there, we will have the beam, the AX reaction. Remember, the reaction is acting in this direction, 2400, I have AY. AY is 800, we calculated before. I have the distributed load. Remember, we have to carry everything that is with the load within the section. If I make a cut here, it's exactly that. It's like getting a scissors here or a knife, cutting this. If I cut this, I have load on top of that. So that has to be there. And this is the point D. Because I'm using this side of the element, then that point B, my shear is going to be acting in this direction, and the moment is going to be acting in this direction. I'm sorry, it's not going to be acting in that direction. Those are going to be the positive directions for axial at D. That's going to be the positive assumed directions for my internal forces, shear, moment, and axial. Now, once again, if you are here, you need to know this height of the load, because you know this height is 200 Newton meter. You can see it here. This is 200 Newton meter. This is 400, but now I'm here at this point. How do we calculate that? Well, it's easy, because if you look at closely, this is just a ratio. If I make a rectangle from here to here, remember this is 200 and this is 200. Then I can say 200 is at 6 as 3 is at this height, and this height is going to be 100, and 100 plus 200 is 300. Or I can say, oh, wait a second, this is 200, correct? Yes, because this is 200 here, and I'm exactly at the middle of the distance, and this is a straight line. Then here, this height has to be exactly half of this height here. So this is 200, this is 100 plus the 200. That means that the total height is going to be 300. But what I'm interested in is this triangular part is 100, and the bottom part I already know is 200 Newton per meter. Newton per meter. And once we have that, the rest is just nothing. It's just, once again, doing summation of forces and summation of moments. Now, pay attention to this, because in this case, once again, I have a load coming from the triangle. That load is going to be 100 times this distance, and this distance is 3 meters, because this is where the point D is, if I'm not mistaken. Let me see. Yes, 3 meters here. So it's going to be, this force is going to be 100 times 3 divided by 2, which is 150 Newton, and this load for the rectangle is going to be 3 times 200, which is 600. The location of the forces again, the rectangular at the centroid, which is half of the rectangle, and that is 1.5, and the 150 from this end is going to be 2/3 of the base. 2/3 of 3 is 2, or from this end, from the right angle, is 1/3 of the base, and the base is 3, so the distance from here to here is 1. Once you have all the distances, just proceed. Summation of forces in X equal 0. That's the easiest one. Negative 1200 plus AD equals 0, meaning our axial force is equal to 2400 Newton at the point D. Summation of forces in Y equals 0. If we do summation of forces in Y equals 0, then we have 800 minus 600 minus 150 minus V equals 0 for a result for VD equal of 50 Newton. And then we do summation of moments, and you can do here or here. It's easier, usually do it in this side where the internal moment is. Summation of moments at D equals 0. And then I start. If I do summation of moments here equals 0, I have this 800 times 3, and it's going to be negative because remember I'm pushing in this direction and this is the pin, so it's rotating in this direction. So it's going to be negative 800 times 3, and then I have 600, which is going to be positive with respect to this point, plus 600 times the distance. The distance from here to here is 1.5, plus again 150 multiplied by the distance from here to here, which is 1, plus the moment at D. And that gives us a value for moment at D of 1,350 Newton meter. So in this way we can calculate our three forces, or three internal reactions, better said, axial at D, shear at D, and this is the moment at D. Usually every problem for every type of situation when you have to calculate internal forces is done always in the same way. You just have to look for a little bit of trick, the little trick that you have to apply in this. Sometimes you don't even have to apply any trick, but that's what I wanted to bring this problem to you, because in this problem the trick is that this is a two force member. Even if it wasn't a two force member and you have a structure like that and you have a force here, then what you have to do is make a section, treat it like a truss, make a section and separate both sides and try to get forces from one and transfer the forces to the other one, or do the analysis of the joint, or do something. But you can't apply the concept of trusses because you have intermediate forces on the elements. You have to treat this like a mechanism, which is a different situation, but it's similar somehow. Okay, I hope that you like this problem, and see you next time. Thank you for watching.